Welcome to the Cosmic Pie Podcast, episode 26, season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
We do have a chat feature that's running, so if you have any comments or questions you'd like to ask us throughout the podcast, feel free to use that feature. Also, disclaimer, Robert, you want to do one for today?
The opinions and ideas expressed are those of myself and Wayne, not the Department of Physics and Astrophysics, the University of North Dakota, or anybody else. So we're the ones on the hook.
It's like if there's a devil on my right shoulder that says, say anything you want, and there's another one saying, don't say anything.
Don't say anything. Stop right now. Leave it alone.
At some point, the disclaimer doesn't protect you. You realize that.
Yes.
You're still limited in what you can say publicly. So you
Yes.
have to be careful of that.
Yeah.
Now, for those of you who enjoy your podcast, not only on YouTube, but also on Spotify, just to remind you that we do upload to Spotify the next day. So for those, and you have the ability to not only listen, but also watch podcasts now on Spotify. So that makes it very convenient that way.
Yep.
Robert, do you remember last Friday morning at about 4:30? What were you doing? A.M.
I have no idea.
You don't remember? It wouldn't be a good time to go for a walk to the store. Put it that way.
Oh, right. Yeah. The storm that went through.
Yeah. You know,
4:15, I got jarred straight out of bed because the alarms went off.
Yeah, we have a setup here where the telephone rings.
Yeah.
And we have, of course, I have an alert radio, no alert radio, so that was going off for several hours as the storm system was approaching Grand Forks.
Yep.
And then we had a tornado warning, which was west of the city. The television was on with live coverage from Fargo.
Okay.
And even our local KNOX radio station was on live also.
The next day, you posted pictures of the path of the thing, and it passed within under 150 yards of my building. So
I didn't realize that.
Like,
and then so we got to the point where the tornado warning then included the city of Grand Forks.
Right.
So I had everybody up in the house, went into our safe space that we have. And we were sitting in there with our two dogs. Everybody's got to be safe, right? With the radio and stuff listening, and the phones. And the phones, at some point, I think it was 15 minutes or something, and the phone's like, okay, now the tornado warning has moved to the east of us.
Right.
Because storms are going west to east. So that was over with, right? But in the meantime, the sirens went off. You could hear the sirens blaring. Of course, you could hear the wind howling outside. And when you peeked out before we went into storm shelter, the trees were bent like on a 90-degree angle. Right? It wasn't a good time to be outside, put it that way.
No, it wasn't.
The only thing I didn't see really was hail. That was the only thing I didn't notice. So, then the tornado warning, passes by, and it's like, basically it's all clear. The sirens stop blaring and stuff. So, you can go back to normal in that sense.
Right.
And it wasn't until the evening of that day later on. So, no, that would have been Saturday. Sorry. It was the next day, Saturday evening, that the report was released publicly. It was in our local newspaper. There were actually 4 tornadoes touched down in the county, Grand Forks County.
I didn't realize there was that many.
Yeah, and one of them actually went right through the city, and they had a path, like the track of it on a map, which is what I posted, and that's what you saw.
That's what I saw.
And I've been living here 18 years as I posted. And this was the first time in those 18 years that a tornado actually touched down and went through the city proper.
Right.
We've had them outside the city, but not through the city itself.
And all I can say is it couldn't have been much of a tornado, because not that any tornado is something to play around with, but there were no trees down in my neighborhood. And like I said, it passed within 150 yards of my building.
Yeah, so all 4 of them were EF1, so they're on the weaker side. But still, if you get hit directly by it, I'm sure you're going to notice.
You've got problems.
Yeah. And there was damage done outside the city. So there was like a piece of wood went through somebody's bedroom wall and ripped off part of the roof. And luckily they didn't get hurt, but someone got injured in a separate sort of tornado also that night. So you just never know. But that was pretty close.
Mm-hmm.
Pretty close.
I think that's the closest I've ever been to a tornado.
Yeah.
I've been around some straight line winds and things like that, but I think that was the closest I've come to a tornado.
And the one thing I run for is go outside and look at my fence when it's daylight. Because when that snaps off and you have to replace poles and stuff, that's a real bugger. That's hard, especially in the summer where it's hot and humid.
Yep.
Oh, it's a lot of work effort. Of course, I'm cheap. I don't hire anybody to do it. I do it myself.
Oh
Anyways,
yeah, yeah.
yeah. So speaking about showers, there was a shower last night, and actually proceeds even to tonight. So another
Yep.
opportunity to look. And this is the annual Perseid meteor shower we talked about last day. I just want to make sure that people realize that's happening right now. So tonight it's still a good night to look. If you go outside after it gets dark, of course, depending where you live, hopefully it's clear. And I'll see that you don't have much smoke in the air from forest fires. And we do have that around here. The other thing, of course, is the moon is fairly bright.
Right.
And the moon rises fairly early. Now, the later you can wait in the evening, the better it gets because the meteors are coming from a certain region in the sky associated with the constellation Perseus. And it's just because that's the sort of track that the particles left over Comet Swift-Tuttle and its orbit around the sun deposit the fine particles along that orbit, and the Earth hits that debris once a year, and it just so happens that the direction the stuff is coming from is towards the constellation Perseus.
Right.
And so when this constellation is highest in the sky, which is very late, just before dawn essentially, you're going to see typically, more of the shooting stars than you would normally see.
Yeah.
But then you got to put up with the moon. Now, last night was also a good night.
Mm-hmm.
And so I checked a few times throughout the evening. In fact, earlier in the evening, it clouded over a bit here in Grand Forks.
Yes. That's why I didn't bother to go see.
Right. So I looked several times throughout the evening, and I'm an astronomer, so I'm up all night, as I joke, working. And so I peeked out at about 4:30.
Okay.
It had cleared up. The moon, of course, was really high in the sky, so the sky was really bright. We had a little bit of smoke in the sky, and you can tell that because the color of the moon was different than what it should be. And when I went out, I stared at the sky just off the constellation Perseus for a while. And it was only within 5 minutes. And Robert, I never told you this, so this is new. I seen one of the brightest Perseid meteors I've seen in years. So bright you could easily see it. Easily. I mean, it just caught your attention. And it left a long trail that just lingered for a few seconds behind it.
Nice.
It was extremely bright. In fact, I would love to have seen that shooting star when there was no moon and you're in a nice dark side. It would have been extremely bright.
Right.
So, and that was the only one I saw. And I only was out for like 20 minutes in total.
But you'll see a lot more of those during one of these big meteor showers too.
So the thing I want to stress is, even though the sky might be bright because of the moon in other situations, like smoke in the sky, it'll be harder to see. You won't see the fainter shooting stars, but you can certainly occasionally get these really bright ones.
Right.
And so it's well worth going out to have a look. So.
Absolutely. And like Wayne was saying, the later you can stay up, the better it's going to be. Perseus is going to start being at zenith and less atmosphere then to go through for them, less distortion, less just sky brightness.
Yeah, I mean, the only thing this time of the year you watch out for around here anyways is mosquitoes.
Yeah.
They carry West Nile.
Yeah, and
you just don't know which one is contaminated or not, so you don't want to take a chance. So put on
deep
repellent,
woods off.
and cover up as much as you can stand in the warm temperature.
Right.
I mean, in the past, I've had situations where we laid on lawn chairs and stretched out, on lounge or lay down on a sleeping bag on the ground or whatever, and look for the Perseus and count them up. We used to do that as a younger child.
Right.
Some of them in an hour, you get up well over 100 on good showers.
Cool.
In fact, I recall back in the 90s, there was a prediction it was going to be a really good Perseid meteor shower because Comet Swift-Tuttle had just gone by and deposited fresh material along its orbit, and the Earth had hit that. And we had a prediction would be a lot of these fireballs. And sure enough, I remember where I was living, wasn't around this area, that where I was, it was foggy. And I actually had to drive inland for a bit, basically about an hour's drive, and got to a nice clear spot. And it was well worth it. The fireballs that were coming down left and right, I've never seen that ever in my life.
Cool.
It was amazing.
Nice.
And I wish I could share that with everybody. Like someday we'll get back to that, depending on the orbital mechanics of the comet. And it'll be amazing. Hopefully you'll have clear skies wherever you are when that ever occurs again.
Right.
So it was really cool. Now, the other update I wanted to mention is we talked a lot, and there's been a lot. Now, Robert?
Yeah.
Okay. We've had this discussion in the past about your feelings related to science communication.
Yes.
Now, this is a Hubble Space Telescope image that was taken in late July of our new visitor to our solar system, this comet 3I Atlas. Now, from its orbit, we can tell that it's not bound to the sun. It's not in what we call a closed orbit, an elliptical orbit.
In fact, it's in a high energy open orbit.
Yeah, so it's in what we call a hyperbolic orbit.
Right.
Which means it has enough velocity that it comes inbound, goes around the closest point to the sun, and then back out again. There's no way that the sun is able to halt it from escaping the solar system.
Right.
Now, from the point of view of science communication and doing a disservice to the public when we say things that are not factually
absolutely
correct or
I
have
agree.
backup. Do you know what I'm getting at? I don't want to mention the person's name.
I don't know the person, but I know what's all being said about this comet.
And maybe you should say what I'm going to say what you think, what you know here.
Oh, it's an alien spacecraft. Yeah. No, it's not.
So there's a certain individual that works at a university, prestigious tier 1 university, Ivy League school university on the East Coast. And I'm not going to say the university or who it is because I don't want to get in trouble.
Yeah.
And this person has done countless number of interviews. You see him all over the place talking about this object. And he makes it so that, and because he is a full professor and should know everything that's going on, you think he's an expert on this, is trying to get people to believe that this is an alien spacecraft, as you mentioned. Now, every observation that's been done at this point with multiple telescopes indicates that this is definitely a classical comet. In fact, the image that you see here, you see a bit of a tail that's sort of in the upper.
You see the tail developing.
Yeah. So there is absolutely no evidence at all that it's an alien spacecraft. You know what they say, Occam's razor. You want to mention how you use
Occam's
that
razor says that given more than one scenario, more than one solution, the simplest is the correct one. So, we've got this idea that it's a spaceship or an alien probe or a comet. It's got a tail. It's not slowing down. The easiest solution is it's a comet.
Yeah. So, which would it rather be? Just a natural comet or an alien spacecraft that's dressed up to look like a comet just so we wouldn't notice the difference? Come on.
Come on.
What's it more likely to be? Think about it.
It's more likely to be just a comet. Yeah. And if it's an alien probe or spacecraft, why isn't it slowing down? If it starts making course corrections, now I'm more inclined to believe this is an artificial object. It's not. It's coming screaming in.
But why do you have a scientist at one of the top schools in the world, not just in the United States, spouting a bunch of quote-unquote crap?
To stay relevant?
To stay in the media?
Yeah.
To get all the
like
hype, fame, and fortune? Is that the idea? I mean, what other motivation is it?
That's all I can think of. I mean, I don't, honestly, I couldn't tell you who you're talking about. But the only thing I can think of for saying things like that is because you are a rising star or something like that, which kind of narrows it down to who it could be. And your star is kind of dimming, so you're trying to stay relevant. You're trying to build up a big deal about it. And they would probably argue that really all they're trying to do is generate a conversation. Well, there's there's better ways to generate a conversation about this object than trying to say it's an alien spacecraft.
And if you actually listen to this person who's been on CNN, for example, they are definitely pushing that idea that it's an alien spacecraft.
Yeah, no.
And they come up with some facts which are just not right. I mean, the object is really far away, several astronomical units away. An astronomical unit is just the average distance between the Earth and the Sun. So it's several times the Earth-Sun distance away from us. And because it's relatively far away and the object is relatively small compared to like a typical planet, it's very faint, and you need large telescopes to see this thing. And so it's hard to get really good, precise measurements because it's so faint. But that opens up a sort of an uncertainty in what it could be in terms of its absolute properties. And they pigeonhole their way through that opening and say, it's got to be, or most likely will be, or at least we're implying it is, an alien spacecraft. It's like, come on.
Come on. It's outgassing. It's got a tail. It's a comet. Come on.
Now, the HST image that you see here, from that you can estimate the size of the comet. And because the coma, is not sort of a on and off in terms of the physical size of the comet, it's diffuse. So
Yeah.
as the light sort of spreads outwards from the comet body itself, it's harder to determine or estimate what is the actual size of the comet. So now the size of it is fairly uncertain at this point. It will get better as the comet
Gets closer,
gets closer, and we have hopefully a better view of it. It's on the order of about 0.32 to 5.6 kilometers, so 320 meters to 5.6 kilometers in diameter.
Here we go.
But that's a typical size. That's not unusual for
That's-
cometary size.
Yeah, that's a normal size comet.
Yeah.
You know.
The only thing that's unusual about it is it's just a third object that we've detected. And one of those other objects, the other two, was definitely a comet, Borisov. And the one before that, Oumuamua, was more of an asteroid than a comet and more elongated in
Right.
terms of its shape than what comets typically are. This is the third object we've seen that came from outside of our solar system. And once again, it's a comet. So it's probably a comet or an asteroid when
Right.
we do see these objects. In
And-
fact, yeah. Go ahead.
I'm just going to say that we've only recently got to where we can identify and spot these objects. So it's not surprising to me that we've, in a fairly short amount of time, have spotted 3. We've just gotten where we could.
Yeah, these objects, number one, are really faint. Mm-hmm. And so to see them, you really want to survey over a huge area of the sky.
And they're moving really fast.
And they're moving
in
fast.
and out of the solar system in a matter of months.
And I've seen speculation also online that this comet is moving really fast. But if it came from another star system, it had to have an origin somewhere. If it came from another star system. In
Right.
fact, it could have been leftover debris in interstellar space. That's still a possibility. But either way, this stuff is all moving around the center of the Milky Way. It's an orbit around the Milky Way. And the sun itself travels well over almost 500,000 miles per hour in
Right.
its orbit around the Milky Way. So if this object came from another star system, for example, it always already would have that initial speed from that star orbiting the Milky Way. So it's going to have these speeds of hundreds of thousands of miles per hour. That is not unusual. We'd expect that.
We'd expect it. I mean, even beyond the relative velocities of the 2 star systems, if it came from another star system, it would have had to have been kicked out of that other star system, so it would have an even higher velocity.
Yeah, in a way, maybe it came too close to a giant planet in that star system, picked up some momentum, some energy, and it was enough to reach escape velocity, and it left that star system. But that could have happened, 500 million years ago, for all we know.
Right.
And then it was traveling through interstellar space, I should say, since that time. Never got really close to any other star, so it's not going to lose its volatile material because it never gets warm enough to start evaporating.
Right.
And maybe this is the first passage nearby another star.
And it's picking up momentum from our star.
Yeah, it's pulling it into gravity,
know?
speeding it up.
So it's going to, if it hits another star system in the far distant future, it's going to be going even faster through it.
So there's nothing unusual about this object, and certainly nothing that would motivate you to then go on in the public
And say,
and say that it's probably an alien spacecraft. It's like, come on.
there's nothing to point in that direction at all. So, yeah.
Now, the other cool thing that's happening right now, so if you can, please look at this tomorrow morning or as soon as possible. And this is what we call a conjunction. So the close passage, if you like, in this case, of the planet Jupiter and Venus. Now, I also saw this last night when I was out at 4:30. I didn't want to mention it then because I wanted to mention it now to talk about it. And I've been watching this the last several mornings.
Okay.
And you can clearly see the relative motion of Jupiter and Venus to each
Cool.
other. So their positioning are constantly changing every day. So they're really close together. So you need to get out and have a peek if you can. It looks really, really neat. And
I had a peek last week because I was giving a ride to a friend of mine. And so came home at about 4:30, and I was like, okay, that's Venus. Gotta be Jupiter. So I recognized it for what it was, simply because there's no two objects that look like those.
Yeah. So it's a really cool view. In fact, last night when they were rising, I noticed they looked a lot redder than they normally would because of the smoke that's in
Because of
our
the smoke.
air. So
Yep.
that's another indicator that we definitely had some high smoke around. But it's
Yay.
worth the view. So get out there before the sun gets up
Yep.
and have a good peek at that.
Wake up an hour or two earlier, go out, look,
And then go back to
enjoy
bed.
it, then go back to bed. Yeah.
Okay.
So
That-
the next one.
Yeah, you see, now here is an image taken by the Perseverance rover on Mars. Now,
Okay.
what strikes you as weird about this image?
Do I have to limit it to one thing?
Yeah, just one thing.
Okay, well, the sky is far too blue.
Yeah, it's almost as if you're on Earth, right? In some
Right.
desert region. Now, I just want to emphasize that this image has been altered. People will get upset over NASA, they have in the past, for using enhanced color images or pseudo color images where the colors have been changed from what we would normally see with our eyes just to bring out subtle features and not say anything in the figure caption.
Right.
And people got upset because they said that's not the color it should be, or NASA was implying that that's what it is because they didn't say the difference. So they clearly tell people on this panoramic view on Mars that the reason why the sky is blue is not because the sky would be blue if you were standing there with the rover. It's just that they had changed the color to bring out the features, the contrast between the land and the sky. So they
And-
wanted to look at the different mineral compositions in the ground and the soil and the hills and the distance.
I was about to note, you can tell this is a color enhanced image for other reasons too. Everything is too blue.
Mm-hmm.
You know, that sandbar on the right side, that sandy arc, is just too blue. Things don't look like that.
And the other thing is you can see part of the structure of the rover, especially on the left, and that's all blue.
And that's all blue. So this is obviously blue enhanced all through the whole thing.
Right. And then some of the things you can see, if you look towards the right side, sort of above that, right below that hill that's on the right, you can see the tracks leading into the distance. So that's the path that the rover had taken to get to
Right.
the position where it's taken these images now. The other thing to notice is sort of off to the left of the center, there's a sort of a white patch, white area. And you can see that.
Oh, okay, yeah. That's
So-
reflection from the sun, isn't it?
No, you would think it
Oh.
is. If you look very carefully in the center of that, so it's really close to the bottom
Oh,
of
that's
the
a
image.
drill hole.
Yeah, it's a drill hole. That's where they drill
Okay.
down, and you can see the little round spot where they drilled, and that's the fresh material that was kicked up from the drilling, and it has greater albedo, higher albedo than
Right.
the surrounding material.
So it's more reflective. So with the blue enhancement, it really pops and shows us.
And that's part of the reason why they did the blue enhancement is to look at these subtle features.
Okay.
So it's
I still don't like it, but
I like
get
it. It's cool. Just think
It's
of
a
it.
cool
Just
picture.
think of it standing there, and you put on sunglasses that show everything in blue, or give it a blue color. A lot
Yeah.
of things. That's kind of what you would see here. But the other cool thing is, you can imagine that you're standing there, and if it did have an atmosphere in the future, maybe terraforming by humans, that eventually you would see a blue sky.
Yep.
And it's also a panoramic that was taken at a time when the sky was unusually clear. That's why they did it.
Right. I don't see much in the way of clouds. I
Yeah.
see a couple of wispy ones there, but you really got to know what you're looking for and
Yeah, and
spend
that-
a lot of time looking at the sky.
And the enhancement brings that out too,
Yeah.
those features, right? So you can see a lot more of the detail than otherwise you would. So I thought this was a really cool image that was released recently.
Yeah.
I love it. You
That's
just
a neat one.
imagine being there, walking on the surface of Mars.
Well, I'm looking at things like how flat and smooth it is in that area, other than the boulders. It almost looks, there's clearly some fluid flow over extended periods that have happened. So I was in mind of glacial flow. Clearly that's not quite right, but then you think about it and it's like, oh, the Martian wind has been blowing across this region for millennia. That's a fluid too.
That's right.
It's worn it all down smooth and glassy.
Yeah. You can almost look there and say, okay, where do I put my ranch? That kind of
Right.
thing, right?
Wouldn't really want a ranch there.
No,
Your cows
but-
would do very
But you think if that
poorly.
was Earth, that would be like unexplored territory. No one has ever been there, ever. Nobody. So it looks beautiful in that sense. It's
Yeah.
kind of cool.
Beautiful Desolation, I think it was.
You're right. Have Buzz Aldrin talking about the moon.
Yeah.
In Apollo 11. Now, here's a neat sort of study that results have been recently announced. And this is the estimated mass of a black hole that tops the scale at about 36 billion, that's with a B, 36 billion times the mass of our sun.
Wow.
Now, when you look at the image of this black hole, and you can't see it directly, so you see the galaxy that hosts the black hole. Number one, there's an image you can see there on the left from the Hubble Space Telescope. And the thing that catches your eye right away is that horseshoe-like feature, that blue horseshoe-like feature that you see.
Einstein ring.
It's an Einstein ring, almost a full ring. In fact, if you look, maybe take a longer exposure to bring out some of that surface brightness and the faint top there, you'll probably be a complete ring.
Yeah. And what an Einstein ring is it's where you've got a more distant galaxy shining through. The light comes around a foreground galaxy and is bent. It is focused because of the curvature of space-time by gravity. And it gets smeared out because it's not a point source, so it spreads out. Each ray of light from each different part gets bent to a different location. But that blue ring is essentially a much more distant galaxy behind that orange one in the foreground.
And if you want to see this effect, take a glass they would use to, like a drinking glass. Make sure it's empty, of course. And then tilt it up so that you're looking towards a bright light source. And if, let's say, a single source of light, and move the glass away from the light source and then look through the glass as you move it across the light source. And there will be a certain alignment that will take place where you see this ring of light in the bottom part of the glass.
Right.
And then if you move off, then it sort of just see an arc, and then it eventually disappears altogether when you move away from the light source far enough. So this is the kind of bending that happens. Of course, as you mentioned, the bending is due to the curvature of space, due to the presence of the mass of the galaxy that lies in the foreground.
Right.
Compared to the galaxy that's being lensed, as we say.
Yep. It's neat. There's a lot going on in this picture, other than just the supermassive black hole. You've got all kinds of galaxies in the foreground as well as the background. You've got the Einstein ring. You've got, the black hole. You've got now. Let's just go ahead and talk about it. It's off to the side of that foreground galaxy.
Yeah, so the elliptical galaxy that's doing the bending has a redshift of 0.44.
Okay.
Those blue gravitational arcs, and you get a better view of that when you looked at the zoom-in image on the right.
Okay.
That's at a redshift of almost 2.5, as it's labeled there. But there's also another object that you see. There's at a redshift of about 1. So there's multiple objects, not in the same sort of situation, right? Related in terms of the lens.
So that's why that little white square is around that section. It's
and you see that little piece that's sticking out. You see the zoomed in on the bottom right there.
Okay.
Yeah. But one of the neat things about this is, number one, the galaxy that's being smeared, the blue light, you're getting a very good view of it than what you normally would get, because not only is it being smeared, but it's also being magnified, like a magnifying glass.
Right.
And so that allows you to see features like different objects within that host galaxy that lies in the background than you otherwise would be able to see. So it's really cool in that sense. In fact, in the past, we've had these arrangements where people have seen supernovae in
I was going to ask about that.
in these lensed galaxies.
Can you see Cepheids,
I haven't seen that, but I definitely see. I don't think they're bright enough to be able to see them. Not right now. Not with the telescopes that we have.
Right.
But in the future, you should be able to.
Okay.
But you certainly can pick up these supernovae.
Right.
And in fact, we had somebody here at our department a few years back talking about this from the University of Minnesota.
And the reason I'm asked about Cepheids is, of course, again, their brightness is their mass and their brightness is intrinsically linked to the rate of pulsation. And so you can use them as a standard candle, which will give you then the distance, because light drops off as 1 over the distance squared. And you'll get, another measure of the distance. So
And of course, if you find a supernovae type 1A, which is an exploding white dwarf,
there's the third.
that's another way of measuring distances. So if you can capture one and just happen to be looking at a time where it's brightening and get the light curve, the change in brightness with time, then you can estimate then what is the distance to that supernova based on how bright it gets in terms of its peak brightness
Right.
and how it declines in brightness over time.
And so that's three avenues to the same measurement. And I tell you, we scientists love that when you can get multiple measurements that are independent of each other, but they point to the same value. Oh yeah, that's where it's at.
In fact, it was the noticing the difference in distance that you measure by using the redshift of a galaxy and the distance you get by looking at supernovae type 1A, these carbon detonation supernovae, these white exploding white dwarfs, that provided observational evidence for the discovery of dark energy in 1998.
There you go.
That's where that came from.
Absolutely.
So, yeah, you never know what sort of profound information and what impact it has on science when
Right.
you do these type of observations. Now, the mass of the black hole, which is something that can be very difficult to determine, and here's the paper that was published recently about this. How do you estimate that mass? Number one, the obvious one is from the gravitational lensing that you see. And so if you have more mass, you're going to have more curvature of space
And more
at the
lensing.
same distance away from the object. And therefore, you're going to see that in the lensing features that
Right.
you measure from those images that we showed in the prior slide. So by measuring precisely the shape of the lensed galaxy can give you an estimate of the mass that's contained within the region of the lensing. In fact, that was used a lot over the years to estimate what is the total mass of a galaxy cluster. And then you look at what are the masses then of the individual galaxies, the ones that you see, and you can come up with estimates of them based on how bright they are, knowing the distance to them and so on. And you find out that there's on the order of several times, in fact, up to 5 times more mass in the galaxy cluster that you measure through these gravitational lens features than what you get if you just add up and sum up individually the masses of the galaxies themselves.
Right.
And that was evidence for dark matter,
Right.
because it's the combined matter, ordinary matter plus dark matter, that gives rise to the gravitational lens features. So that would give you an estimate of all of it, where if you just look at the individual galaxies and based on how bright they are, that's normal matter, like stars, for
In
example.
fact, weren't they looking at that specifically to try to naysay some of the other evidence that had made people say dark matter existed? And they were trying to say, see, no, it doesn't.
Yeah, well, one of the early evidences for the flat rotation curve.
Right.
So that's Vera Rubin and Ken Ford and others that worked on that for many years. And then you can expand that out. For example, when you measure galaxy clusters, let's say at X-ray wavelengths,
Right.
you'll see that they are very bright X-ray emitters. So they contain hot gas. And from the X-ray emission, you can estimate what is the temperature of that gas that gives rise to those X-rays. And that temperature is on the order of like 50 million Kelvin. So it's very, very, very hot gas.
Right.
Well, what does hot gas like to do? Expand.
Expand.
Well, this gas is trapped in the galaxy clusters. So that means it's trapped there by gravity. And if you think of Einstein, that means there's a certain amount of mass there that's curving space so that gas cannot escape. And you can estimate from that measurement what is the total mass in that galaxy cluster. And once again, it's about 5 times the total amount of gas that you get if you just add up individually all of the gas,
Right.
all of the galaxies that's in that galaxy cluster. Once again, it's evidence for dark matter. You can look at the leftover heat from the Big Bang, the cosmic microwave background. You can see features in that distribution of the temperature correlations in different parts of the sky. And those do not make sense, those statistical type measurements, unless there's a lot more mass in our universe than ordinary matter. And the amount of mass you need to be consistent with the observation is 5 times the amount of ordinary matter.
Right.
Evidence for dark matter. The bullet cluster is a classic example of evidence for dark matter. It's all over the place. And in science, I mean, we had a thing, someone made a comment, I don't think dark matter is a real thing. And some people say, I don't believe, and all this. I don't believe anything either.
Right.
right?
But the
Unless there's
evidence is there.
evidence, right?
The evidence is
I don't believe my wife loves me. I just know when I go home every day after work, she doesn't lock the door before I get into the house. So there's evidence that she loves you, you see?
Right.
So that's the thing.
Yes.
And I'm talking about science. I'm not talking about religion here. I'm talking about science.
Right.
So in science, you don't believe anything. You look for the evidence. You think of a galaxy that's on the other side of the observable universe. Do we believe that light operates the same way in terms of the emission from different atoms as electrons transition the energy levels? No, we don't believe in any of that. We look for the evidence, the observations, and all the observations that we make show that the atoms work the same way they work locally, nearby.
as they do there, or vice versa, there as they do here. So, unless something changes that says the laws of physics change as you go to different regions within the universe, the evidence is there. There's all these factors pointing, like I mentioned earlier, to the same conclusion, and they're not interrelated. So you've got one conclusion. If 5 things are pointing at the same answer, there's something going on there.
And the other neat thing is if we discover that there is no dark matter
Right.
in the future, then our discovery that we make has to explain all of the observations that we have up to this point.
Right.
You can't dismiss those observations. Anybody with the right equipment can go make the same observations, not like we made them up.
Right.
So that's the thing. You can't just say there's no dark matter and that's it. You have to explain why then do we observe all of these things
Right.
that points towards the existence of dark matter.
There we go.
You have to explain those away on a scientific basis.
Yep. Because things don't just happen to happen.
Yeah. But the interesting thing about this object then is the fact that its mass is so great, 36
6
billion.
billion.
And the thing that really catches my attention personally is how do you form such an object?
Right.
How does a black hole of that huge mass actually form?
Yeah. And as far as I know, there's no good answer for that because, I think the top running is direct collapse.
Yeah, so here's the conundrum that we're in. There are stellar mass black holes, so black holes that come from the end state of massive stars.
Mm-hmm.
They would typically have several solar masses of material, up to tens of solar masses of material. In fact, we don't have to guess on any of this.
Right.
We can turn to LIGO and gravitational wave detectors.
Right.
And by the way, that brings up a sort of a little bit of a tangent here that I'm going to say something. Do you realize that one of the LIGO detectors may now be shuttered because of the budget
cuts.
proposals, the proposed budget cuts to the National Science Foundation?
Yep. I've been expecting to hear that. I'm expecting to hear both of them are going to be shuttered.
I mean, it just doesn't make sense, right? It took all the way till 2015 to advance the technology to the point where we can start to detect gravitational waves. It gives us a new window to the universe.
Right.
And we need to pinpoint where these objects are located when we do detect the gravitational waves, and essentially by triangulation.
Right.
So we need several of these detectors that are observing the same signal in order to figure out what direction the signal came from, and then to isolate what the target is. Mm-hmm. What is the progenitor, if you like, of these gravitational waves that we detect. To close one of the LIGO detectors when we're just starting is unreal.
Right.
It's like recalling Columbus after he left the shore of Europe about 100 miles, say, that's enough, get back, we've taken away your budget.
Right.
This kind of thing, right? It just doesn't make sense at all. But, I mean, there's a lot more other things. I mean, money is tight. I mean, the United States is 37 trillion in a hole. It's not like we have money growing out of our ears. I get it. But we should be a little bit more careful on what we're willing to spend money on because we're mortgaging our future away.
Well, when the total science research budget, this is research of all types, only amounts to 3% of the federal budget. Cutting research, scientific research, folks, is the couch change. You're trying to balance the budget by finding the quarter in the couch. Come on.
And the other thing, look at the inspiration for young people.
Right.
You know, so where are we going to get our next scientists from and develop technology? And in this country, of course, you want to compete with other countries to stay ahead. How are you going to do that if you cut all the budget for that stuff?
Right.
You're going to get left behind.
And exactly. And that's what's happening, to be honest.
Yeah, it doesn't really make a lot of sense to me. But anyways,
it's been happening, and it's going to accelerate and get worse.
I'm not a politician, so it's like I don't know what goes on in the background, right? All
Right.
the wheeling and dealing, but we'll see how it plays out in the future. But yeah, so 36 billion solar mass is nothing to sneeze at. It can't be a core collapse supernova would create such an object.
Right. And it can't be the combination, the it can't be them sucking into each other. Merging. That's the word I was looking for. Thank you. Yeah, it can't be merging because there's lots of energetic reasons why they don't just merge into each other.
And another thing that sort of helps this explanation, hopefully, is the fact when we look at the center of almost every normal galaxy, including our own Milky Way, they have these what we call supermassive black holes.
Mm-hmm.
So our Milky Way has a black hole, has a mass on the order of about 4 million times the mass of our sun. And we get that from, number one, we've directly imaged it. We know it's there with the Event Horizon Telescope a couple of years ago.
Right.
So we've seen the shadow, if you like, of the black hole at the center of the Milky Way. But before that, and we can do it today still, we can watch stars orbiting the very center of our galaxy.
Right.
And based on simple Kepler's third law of planetary motion.
Right. So don't even have to get into general relativity.
No,
here.
this is from
just Kepler's motion from the 1600s.
From the 1600s, we can estimate based on how fast something is moving in its orbit and what type of orbit it has, how long it takes to complete that orbit, what is the mass involved that this object is orbiting around? What's at the focal point of my elliptical orbit, let's say?
Right.
And from those type of measurements, and we got more than one star, there's several stars that we followed over many years. In fact, people have won the Nobel Prize in physics for doing these type of observations with Keck telescope and others.
Yes.
Yes.
Yeah.
And what they discovered is, that's consistent with the orbital motion of these stars is consistent that the thing they're orbiting has a mass of about 4 million times the mass of the sun, and yet there's no light coming from that area.
And it's in an area of the space that's only, something like what, 0.2 parsec or
Yeah, it's
something?
very, very small
Very
volume
small.
of space. So what would be, in a very small volume of space and yet emit no light?
And have a very high mass.
I mean, the only thing we can think of is a black hole. And that was prior to the Event Horizon Telescope. Now we directly imaged it. So there's no doubt now.
There
right?
it is.
We see it. We've imaged it.
Well, again, we see its shadow.
You see a shadow, but it's there.
It's there.
Yeah, so the black hole is there. But that's only 4 million times the mass. We got, 36 billion times the mass of our sun to build up to.
Right.
So even there, I mean, some supermassive black holes and other galaxies are a lot more massive, on the order of several billions of solar masses. So how do you get to 36 billion solar masses? We'd have merging of galaxies, and those central black holes ultimately merge together. But that takes time. So you got there's a lot of things that need to occur early on in the universe to build up to this type of mass. That's the interesting thing.
To me, that's the interesting thing. And that's what James Webb is going to be pointing at. So Hubble, I think, was involved with this discovery, but James Webb is even more attuned to doing these types of things. So I think we're in some interesting times in a good way, that there are some things we're going to start seeing and being able to look at that were dreams just a decade ago.
Well, you mentioned the James Webb Space Telescope, so it has discovered these objects known as little red dots.
Yes.
And in these little red dots, we believe they contain these black holes. The interesting thing is these little red dots, some of them had very high redshift, which means these black holes had to form relatively soon after the universe itself formed.
Right.
So that gets back to the idea is if there's a correlation between the mass of a galaxy and the mass of its central black hole. In other words, more massive galaxies are going to have more massive central black holes.
Right.
Where does that correlation come from?
Right.
So is the black hole developing first before material
pulling the
around it
galaxy
creates
in.
into a galaxy?
Right.
Or does somehow in the natural formation of a galaxy you form the seed that ultimately turns into this massive black hole?
Right.
And yeah, go ahead.
We do have a few questions about, this black hole. I don't think we actually have a spin rate for this because measuring the spin of a black hole is quite difficult because there's no surface features. So it's got to have an accretion disk that you can measure temperatures or magnetic fields polarization around. Right?
Angular momentum is what you're after, yeah. It's very difficult. I don't know if there are any measurements of the spin. If there is, I wouldn't trust them, like to be high uncertainty on these numbers.
Right.
So I'd wait a while before I got too excited about it. But they have various angular momentum. I mean, that's kind of the three properties that black holes have, is they have a mass, angular momentum, and electric charge.
Right.
Normally, you would expect electric charge to be zero. They would be neutralized from both positive and negative material falling into overall to be charge balance.
Right.
But certainly angular momentum can vary. There'll be some spinning rapidly and not so rapidly and so on. And obviously you get variation in mass, as we talked about already.
Right.
So this correlation between the mass of the central black hole and the mass overall of the galaxy itself is very interesting. It seems to me if the galaxy forms first, that would require more time since the Big Bang for these supermassive black holes to be created. Yeah. So then if you're finding black holes of decent masses very early in the universe, then maybe that's showing you that the other scenario is more likely where the black holes form first and then the galaxies sort of assemble around it.
Yeah.
So then you could have very early black holes then.
And wouldn't that kind of imply too that it had something to do, the creation of these things had to do something with the Big Bang itself? That it was ripples in space-time or something that maybe caused the mass there to collapse all at once?
Well, think about it. If you have several 100,000 years after the Big Bang, you're getting to the point where objects like a million solar masses can start collapsing and form.
Right.
So imagine you form a clump of material that has a million solar masses and it collapses in on itself, and you're talking about primordial material because there hasn't been any chance for the metallicity to build up, so it's mainly hydrogen.
Right.
And some helium.
Agreed, yeah.
That would ultimately just collapse into a black hole. It wouldn't go through the natural routine of being a star and go supernova and so on and so forth.
Right.
So the direct collapse type of models then could produce these massive black holes very early. And if you have a lot of them in a close proximity, there'd be a lot of merging going on. So potentially you could build up the mass of these things.
And do so rather rapidly.
Rapidly over a period of just a few tens of millions of years, for example.
Right.
So that's why it's important to get these very high redshift, very distant, very early observations from telescopes like James Webb and future telescopes that we'll have, hopefully, to see what is the most distant black hole that we ever observe. Right. Do we actually find black holes that are literally just a million years they existed after the Big Bang? Because that would put extremely tight constraints on their formation.
Right.
And we don't have that yet. But that would be very, very interesting.
That would be that would be neat. That would be neat. Yeah. Or if we could just see these things popping,
Yeah,
anyway.
So a lot to say about this. So we'll see how this plays out. Now, there'll be future studies, of course. That's okay. Studies of that black hole to narrow down a lot of those parameters and those properties to reduce the uncertainties and so on. I mean, so we'll look forward to see what that's like. And there should be other ones out there, not just one, of course.
Right.
So. Now, the other thing that's been in the news is that Alpha Centauri, and that always captures our attention, and the reason for that is the nearest star to our sun.
Is Proxima Centauri, which is part of this system.
Part of the system with 3 stars in this triple star system. It's Alpha Centauri A and B that orbit relatively close together, and then much further out is Proxima Centauri that orbits the two inner stars. And right now, Proxima Centauri is closest to our sun than the other two. So that's why Proxima Centauri is the closest star to our sun. It's a little about roughly 4.2 light years away.
Okay.
So that just means if you're able to go out and the stars in the southern hemisphere, southern sky. So if you're down in the south or something, you go out tonight and you see Alpha Centauri, you look at Proxima Centauri, then the light left that star about 4.2 years ago.
Right.
That's the photons that would enter your eye today.
Right next door, astronomically.
Right. So one of the things we like to do, of course, is in detail to examine this system, because when we get the technology to the point where we'll be able to send spacecraft to other star systems, it's going to be the first one.
It's going to be the first one.
Because it's the closest.
Yeah.
So obviously that's going to be at the very top of the bucket list of places to visit. And so one of the things since basically the middle 1990s, people have started to find evidence of stars, right, having planets orbiting them. And so the whole field of exoplanets developed.
Right.
Today, we've literally seen evidence thousands and thousands and thousands of stars have planets orbiting them. And it made sense, when you think about it, because why would our sun be the only star out of up to maybe 400 billion stars in the Milky Way, not even counting other stars and other galaxies? Why would the sun be the only star to have planets in orbit around it?
Right.
That doesn't make sense.
It doesn't make sense.
So there has to be planets going around other stars, and that's exactly what we found.
Yep.
And so we want to scrutinize, of course, the Alpha Centauri system because it is so close to see if there are any planets there, and that makes it even more interesting. In fact, if we looked with very sensitive instruments and noticed that there are no planets in that star system at all, but another star system that might be, let's say, 8 light years away, had lots of planets, and one of them had mass and characteristics like an Earth-like planet, I think we would probably go there first.
Right.
Or maybe if we could afford it, you send 2 spacecraft. One, and these are unmanned, of course, right?
Yeah.
One would go to Alpha Centauri, and one would go to another star system.
Right.
So having planets then gives you, makes it higher ranked place to visit.
Right. And that's what this is about.
And that's what this is about. So there have been a couple planets that have been seen in this system. And so this is evidence then of a new planet in the Alpha Centauri system. Now, what we see on the far left is just a Sloan digital sky. It's a digital sky survey, not from the Sloan, sorry. A digital sky survey. This was where they took back in like 1950s, the National Geographic Society put money for astronomers to do these plate surveys of the sky. There was one done in the northern hemisphere first and eventually in the south. And that information, those plates were all eventually digitized. They were scanned to make electronic images that people can use. And that's what we call the digital sky survey.
Okay.
And
so
this
that's
is
what that is.
And so that's what this is. So this is of then the Alpha Centauri system. And what you see here is the bright star on the far left is actually light coming from 2 stars, star A and star B.
Okay.
So if we look a little closer at this star system with much higher resolution, which is the middle image that's taken with the Hubble Space Telescope, you can clearly see there are 2 stars, not one. And they're in orbit around each other, as we've said. So we have Alpha Centauri A on the bottom here in this orientation, and clearly Alpha Centauri B at the top. Now, if you zoom in with an infrared camera like we have on the James Webb Space Telescope, and in particular you focus on, no pun intended, at Alpha Centauri A, which is the bottom star, that's the panel you see on the far right. Now, it's very difficult to see planets shining in reflected light from their host star when those planets are extremely close to that star.
Right.
And the best way to do it's almost like an analogy here is imagine trying to see a firefly perched on the edge of a searchlight. You're not going to see the firefly. It's just the searchlight just overwhelms any small amount of light coming from the firefly.
That said, if you study the light of the searchlight for long enough, you eventually get to where you can subtract it out, and now the firefly is evident.
Well, here's what I would say. You measure it with extreme accuracy the brightness of the searchlight, and then when the firefly flies away,
that's another good way of
then
putting
you
it,
notice
too.
that the brightness is slightly less. Or, because we know how fireflies work, they bright and then they go down and they brighten again. So you have this periodic changing in brightness as the firefly is doing its thing.
So you're coming at it from that direction.
Yeah,
Okay.
I can notice that. So what you could do here, of course, if you can accurately model, first of all, you mask out, and we'll show that in the next image, you mask out the light coming from the host star. And when you subtract it as best you can, what's left, hopefully, is something that's not an artifact, but actually, in this case, a planet. And that's what you see labeled S1 in that far right panel. Now, it's interesting to note that Alpha Centauri A, and you can figure out its properties by looking at its spectrum. So spectroscopically, it's a G25 star, so spectral type G2, and it's on the main sequence.
The V means main sequence.
Right?
Yeah.
And it's a main sequence star, so what's it doing in its core? Happily converting
Hydrogen into helium.
Hydrogen and helium, just like what other star?
Our sun.
Just like our sun. In fact, knowing that it's a G25 star, it's very close to the same mass as our sun.
Right?
And there's a little bit of spread in the masses of those spectral classes. So detailed spectroscopic analysis puts the mass of Alpha Centauri A at about 1.1 solar masses. So it has only 10% more mass than our sun. So it's definitely sun-like.
Yep.
And if you convert that to luminosity, which is the L value there, it's about 1.5 times the luminosity of our sun because it has that little bit more mass.
So for there to be Earth-like planet, you'd have to be a little further away.
A little further away. But it's definitely a very interesting target because it's
Absolutely.
sun-like. And you'd want to go there and investigate it.
Now, it's a member of a binary as well, so that would seem to make it uninteresting because up until recently, we would have thought that the gravitational pull of two stars would have made it impossible for planets to form. And we've since found out that that is an error.
And that reason for that is because we had only one sample to look at,
Right.
and that was our own solar system.
Yep.
And you know the problem if you have a sample size of one and trying to make some general characteristics about objects.
Your error bars are huge.
Right.
They're indeterminately huge.
Exactly. So with closer view, and this is using an instrument on board the James Webb called MIRA, so the mid-infrared imager. The raw data, if you like, is on the far left. And notice how bright, this is the combined light at infrared wavelengths of both A and B. So it's a real mess. You can't see anything. Plus they're saturated in the image. You see all these big diffraction spikes sticking out everywhere or nearly saturated. And you got these artifacts from every star due to the fact that you have multiple segments of mirrors, the way the James Webb was built to be able to get into space on the rockets we have available today. It had to be folded up a bit and then open up almost like an umbrella in some sense. That causes these artifacts, as you see, as these big spikes coming from the stars themselves.
Yep.
Now, when you subtract off those effects, you get the middle panel. And Alpha Centauri A is in the bottom, Alpha Centauri B is up top, illustrated by those yellow star-like symbols. And the brightness, those objects have been, the light from those stars had been removed.
Mm-hmm.
And if you focus on then Alpha Centauri A, which is again that panel that's on the far right with the proper modeling of the light distribution that's left, and then subtract that off, then you see the presence of that object S1.
And I will also point out, it does say that on there. It's a candidate planet.
Yes.
How would we take it from being candidate to a known one? We'll come back, make the same observation in a year, 2 years, and that S1 should still be there, but it should have moved in a very predictable Keplerian pattern
In
form.
fact, one of the things when you look at this, somebody could easily say, how do you know that's not a background star, a background object? Because they looked at images taken over several different time frames and saw motion in S1.
There we go.
They already
That's
have
what we're
that
talking
done.
about. So they're
Was
starting to do that.
Those observations were made before this paper was published.
Nice. So the confirming observations have been made. It's just they haven't been written up yet.
Yeah, well, the thing is, this is part of this paper, but
Okay.
it's just that you want more evidence to be sure.
Right.
So they're going to be waiting
So-
for follow-up.
Yeah. Are they trying to get any radio? Well, no. The binary motion would cover any radio velocity signal.
You can do the same thing. You can watch it for an even longer period of time
Okay.
and see if it displays Keplerian type orbit. All you
Right.
know is that it has moved
Okay.
from one observation to another, taken over a certain time period. But you want that time period to be a lot larger.
So that you can see that it is
Yeah,
Keplerian.
exactly.
Yeah.
And not just happen to be nearby passing some type of proper motion
Yeah.
that's unrelated to, the star
The
itself.
bottom line is early 1600s, Kepler came up with his three laws, and we're still using them, even though we do have general relativity that would be more accurate. But GR is also much more difficult with the math.
Right.
So
So the thing is, if you want to understand how we can determine the mass of these objects, in other words,
Yeah.
where does Kepler's laws come from and how do they work in nature, these are the type of things that you would explore then with higher education, for example. So we always like to Tell people that if you'd like to learn more about whatever subject you're studying, it doesn't have to be any type of science or math. It could be in the arts, humanities, whatever. Then go to higher education. There's lots of opportunities out there, including here at the University of North Dakota.
Yep.
So
And you can do a lot of them online here at North Dakota. So, yeah.
very convenient. You could be in an ice shack in Alaska, northern Alaska, have nothing to do all winter because you can't go outside. It's just too cold.
Kind of like here. No, bad rub.
And you could take programs online. As long as you had a Starlink or some internet connection,
Yeah.
then you can educate yourself. And then, yeah.
Absolutely.
So always have those. And of course, you can come here as well on campus and take programs.
And come talk to us.
And come talk to us. We are
Yep.
here. Now, our next podcast will be next Tuesday. That's August the 19th.
Mm-hmm.
Same great time, same great location.
And say it, yeah, time and location, and yeah, okay.
Did I cover it all?
I think
space-time coordinates?
I think that gives us space-time coordinates.
And of course, we always put up right after this podcast is a link to the next podcast, so you can bookmark that so you don't miss us. The other thing we do is we leave a quote at the end of all of our podcasts. So
Okay.
today, because we have talking a little bit about Mars,
Oh,
and
okay.
shown some image, I decided to have a quote from Percival Lowell.
All right. I
Who-
wondered if that would be who it was.
Yeah, he was associated. I mean, he was born in 1855. He passed away in 1916.
Yep.
And at the time that he passed away, he was a rich person. He was going around giving talks, basically trying to convince people that there was life on Mars, to the point they actually had canals and dug ditches and did irrigation systems and things of that nature.
Right.
And if you actually look at Mars with a ground-based telescope, you do see some linear-like feature. It was only, I think it would be in the 1960s that we flew by one of the Mariner spacecraft, flew by Mars, and got some detailed images that it was all covered with craters and so on, that there was no evidence for life creating canals and all of
Canals and
these
so
kind of
forth.
things.
Yeah.
So there's a whole history behind it that we could go in someday and talk about.
Yeah,
You know,
we
Martians
probably
and
should.
where does all that-
Schiaparelli and all of these
Yeah,
guys.
where does all that come from? So the quote from Lowell today is that Mars is inhabited by beings of some sort or other we may consider as certain, as it is uncertain what these beings may be.
Cool.
So he was definitely convinced right up until he passed away.
Yep.
And of course, and you can't blame him. Of course, today we have the space age. We can go to Mars. We can land on its surface. We know what's there. And when we look, you take that panoramic that we showed earlier of Mars. I didn't see the golden arches anywhere, for example. So as far as we know, there's no creatures. I didn't see like a deer running across the field of
Right.
view or something like that. So as far as we know, whether or not life has arisen on that.
Mars at
In
some
fact,
point,
I think I'll put a shameless plug for Robert here. He has you want to mention it, a video online where he talks about
Where
life
I
elsewhere.
talked about a little bit about life elsewhere, and it's on my. I'm trying to be an author, so it's on my author social media page. But yeah, I talk a little bit about my views on life elsewhere, and maybe we'll get around to doing it here. It's come up often enough. We may want to try it.
Yeah, for sure. Anyways, for those who are watching, please give us a thumbs up. So smash that like button, as they say, but don't break your
Don't break your thumb.
computer or your device in the process.
Yeah.
And if you haven't subscribed, please consider subscribing. Tell all your friends what a great podcast this is.
Yep.
Hopefully that's how
Hopefully
you think of
that's
it.
your view.
And we'll see you next time. Thank you
All right.
for watching.
Have a good night, folks.